Taylor polynomials are one of those topics that, once you know what it's all about, really isn't that bad, but on a first time through, like you're going through right now, there are some details that can cause certain kinds of hiccups, and so I'll try to make sure in this presentation to point out those details to make sure that the hiccups at least aren't as bad as they could be. So things that we will have to incorporate as we talk about Taylor polynomials are the computation of nth derivatives, factorials, summation notation, as well as working with inequalities. And any of these things, in fact all of these things, aren't that bad, and you've seen some, if maybe even all of them before, but synthesizing them all into one topic is something that can take a little bit getting used to. So let's see what we can do with that. I would also recommend that if the presentation of the Taylor polynomials gets a little bit too lengthy, then I would recommend as soon as we jump to error analysis, you just hit the pause button, start working with Taylor polynomials first, and then do the error analysis separately, because that is another topic that seems to have some intrinsic challenges that we will overcome, but which on first run through can be a bit bothersome. Okay, so with these really just words of caution, I'm not trying to scare anybody here, it's just that this is what I have observed in class. With these words of caution, let's take a look at why people are interested in Taylor polynomials as well as in numerical approximation in general. So let's ask ourselves a very simple question. How do we compute the values of transcendental and or trigonometric functions? Well, so for example, if we want to compute e to the x, what do? Well, we take e, which is this number here. Okay, it's a bunch of decimals, but we raise that to x, right? That's all we do. Duh, it can't be that bad. Well, how do you do that when x is not a rational number? That's actually a question that even if you're really, really good with numbers, you can't answer unless you've got a lot of really, really deep theory, and we're not going to bother with that too much. And the other thing that we have to realize that from a practical point of view, irrational numbers really aren't the only problem, because, for example, would you really want to compute e to the x when x is this 1.4142, right? That's where you have to raise this thing, and then you have to get roots of that, and roots of roots, and all sorts of things that probably, if not totally impossible, are just really, really tedious to work out. And so that means, even though we have computed these values with calculators for a long time, technically we have a problem here, because we need to know where these numbers are coming from. And, well, that's where, of course, Taylor polynomials come in. I wouldn't give this introduction if it wasn't for the fact that we're going to talk about the solution here, right? But the idea for Taylor polynomials is just the same idea as what underlies any kind of numerical analysis, and that is you replace the original problem with a simpler problem, and then hope that the simpler problem solution just works out. So our original problem here is to compute f of x for some difficult function f. And that's hard. And we're going to replace that with the task of computing p of x for an appropriate polynomial p. Now that is an easy task, or if it isn't easy, I mean, there's nothing easy about computing, say, a 15th order polynomial. At least it is easier than doing these strange acrobatics that we've seen would be required for e to the x on the previous panel, right? Okay, so how and why could that work? Well, basically, we need to recall linear approximations, which I presume you've already seen, and once we have done that, we will talk about higher approximations. So the linear approximation, which is just the tangent line, right, of a function at a point A, that is locally a good approximation for the function. Because if we are looking at, let's stop and let's then look at the animation. So here is a function, and the linear approximation is the tangent line. And if we're now zooming in on this point of approximation, then what we can see is, under higher and higher magnification, of course, the approximation looks better and better. And so if we had an infinite zoom here, eventually we would not be able to distinguish this tangent line from the function. And we can already see here, of course, that on this short interval, the difference between the tangent line and the function is much smaller than it was at the beginning. Okay, so this is because, or the linear approximation is a good approximation because the value and the first derivative agree with those of the function at a. That is why the same slope means that near a we have a good approximation. Okay, so now what would have happened if we could have also bent that tangent line to fit the function better, if the approximation didn't just match the first derivative, the slope, but also the second derivative, the concavity? Well, we should get better approximations if we use functions that match more derivatives of the function f at a, and those are ultimately those Taylor polynomials. So let's take a look at how that could work. Here's the function f of x equals e to the x, and here is its first order approximation, that is the tangent line. And the next few approximations, you don't know how to compute them yet, but I just want to show you what these approximations do, because if I now match the first derivative and the curvature, I get a better approximation, right? If I match the first the first three derivatives, I get an even better approximation. If I match the first four derivatives, the approximation gets better. Matching the first five derivatives makes a better approximation, and that hopefully would continue like that. And so the question is, how do we generate the right kinds of higher order approximations? What is behind that sequence of pictures that we've just seen? And so we will start with a point A at which we want to compute an expansion, a Taylor polynomial. And we let n be the intended order of the approximation. So if we want to have a fifth order approximation, n is 5, for example. The nth derivative of the polynomial, the monomial actually, I guess that's a monomial with a center at a. The nth derivative of x minus a to the n at the point a, what is that? Well, let's see, you differentiate a power, what happens is that the exponent comes down and then the exponent is reduced by 1, right? So the first derivative of this will be n times x minus a to n minus 1. Second derivative, n times n minus 1 times x to the a to n minus 2, and so on, and so on, and so on. If you do that n times, well, the n comes down, the next exponent comes down, the n minus 1 comes down, the n minus 2 comes down, all the way down to 1. And of course, if you take n derivatives of this thing, then the exponent is bumped down to 0, which means that overall the nth derivative of this thing is just a constant. It's the product of the first n numbers, and that is something that is also denoted in factorial. So that's the first little potential hiccup that I have talked about. If you've never seen the factorial function, don't panic. This is it. There really isn't much more to be said. We have to get used to it and work with it a little bit, but that's what the factorial function is. Okay, so the nth derivative of this power is just a number. On the other hand, all other derivatives of this thing at a are 0. Because if I take more than n derivatives, well, that just means I'm taking a derivative of a constant and then potentially more derivatives. And those derivatives are all 0 because the derivative of a constant is 0. If I take fewer than n derivatives, I get numbers multiplied with x minus a raised to a positive power. And if I plug a in there, I get a minus a, which is 0 to a positive power, and that's 0 also. So these terms are very nice if I just want to have something that has a certain nth derivative and otherwise has derivative 0. So here, the nth derivative of fna n factorial divided by x minus a to the n. The nth derivative of this term. Now, how is this made up? Here we have to be careful because we're working with the variable in the function, which is the x, as well as with the point of expansion, right? So the variable that we differentiate with respect to is the x, and this here is just a constant. If I take the nth derivative of this thing at a, I just get f to n of a, right? Because I keep the constant, and the derivative of this term here is n factorial, which cancels with this n factorial. So the nth derivative of this thing at a is fn of a, and all other derivatives at a are 0. So this is a prototypical term that would allow us to generate a function that has the derivative of the underlying, the right nth, or the same nth derivative as the underlying function at that point a. if we now add these terms up, so if we form a polynomial Tn of x, which is f of a plus f prime of a times x minus a, right? That first step, that's the linear approximation. If you go back, the zeroth derivative is f of a, so the constant function just matches the zeroth derivative. The first order approximation, the linear approximation, matches the first and the zeroth and the first derivative. And if I add to that now f double prime of a over 2 factorial x minus a squared, then all of a sudden I match the zeroth, the first, and the second derivative, because when I take the second derivative, this term and this term go away, and this term just gives me f double prime of a, whereas when I take the first derivative, this term goes away, and plugging in x equals a gives me a 0 here. That would just give me f prime of a, and so on and so on. So this is a polynomial that would match the first two derivatives, and if I keep going like that all the way to the capital nth term that is built in exactly this fashion, I get a polynomial that has the same first capital N derivatives at a as the function f. So this idea that we had previously, which says find a function that matches the first so and so many derivatives at a of the original function, that is given by this polynomial, and that is a Taylor polynomial, as we're going to record in the next definition. The nth Taylor polynomial of the function f at the point a is the polynomial t capital N of x. It's f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial x minus a squared plus fn of a divided by n factorial x minus a raised to the n. And we can write that in summation notation, and that is another potential hiccup here because we haven't really worked with summation notation that much. It's just another thing to get used to. We simply take those generic terms that we have seen on the previous panel, and we sum them from n equals 0 to capital N. And certainly for n equals 1, this term here also fits that pattern, because for n equals 1 we get f1, the first derivative, at a divided by 1 factorial, which is 1 times x minus a to the first, which is exactly that. And yeah, another thing then, of course, is this notation. I should have said that on the previous panel. That notation just encodes the nth derivative of the function. Okay, so that is the nth Taylor polynomial in summation notation. For n equals 0 to match the pattern, we set 0 factorial equal to 1. That doesn't quite feel right if we think of this as products of consecutive numbers, but it is a definition that just makes sure that this pattern here also matches f of a, because when n equals 0, well, 0 factorial means we've got a denominator of 1. X minus a to the 0th is also 1, and so the only thing that we have left is f0 of a, which is the 0th derivative of the function at a, which is f of a. And yeah. So that is mainly just to assure that the summation formula works for all terms. Okay, now let's just take a look at how we compute a Taylor polynomial, and there are several ways in which we can do that. We could just compute a fixed degree Taylor polynomial. That's the easiest example, if you will. And so let us compute the fourth order Taylor polynomial of the function f of x equals e to the 2x at a equals 0. Well, we need derivatives. The function is f of x equals e to the 2x, f prime is 2e to the 2x, f double prime is 4e to the 2x, f triple prime is 8e to the 2x, and f quadruple prime is 16e to the 2x. Here's where you can see why we ultimately put numbers and parentheses on here, because all those primes get a little bit tedious, of course. We need those derivatives at a equals 0, and so we realize that the function is 1 at 0, the first derivative is 2, the second derivative is 4, the third derivative is 8, and the fourth derivative is 16 at 0. So really no difficulty in principle, it's just more computation. The fourth Taylor polynomial now is the sum n equals 0 to 4 of these terms, nth derivative of f at a divided by n factorial times x minus a to the n, which with a equals 0 is the sum n equals 0 to 4 nth derivative at 0 divided by n factorial times x to the n. And now we just work that out. Well, we can first of all split that out. That's just f of 0 divided by 0 factorial times x to the 0th plus f prime of 0 divided by 1 factorial x to the first plus f double prime of 0 divided by 2 factorial x squared plus f triple prime of 0 divided by 3 factorial x cubed plus the fourth derivative of f at 0 divided by 4 factorial x to the fourth. And that then is, well, 1 over 0 factorial x to the 0th plus 2 over 1 factorial x to the first plus 4 over 2 factorial x squared plus 8 over 3 factorial, which is 3 times 2 times 1, which is 6 times x cubed, plus 16 over 4 factorial, which is 4 times 3 times 2 times 1, which is 24, times x to the fourth. And if we simplify that, we realize that this here is a 1. 2 over 1 x to the first is, of course, just 2x. 4 over 2x squared is 2x squared. 8 sixths x cubed is 4 thirds x cubed. And 16 over 24 times x to the fourth is 2 thirds x to the fourth. Okay, that's about as long as I can draw that out, not for the purpose of making it lengthy, but let's just make sure we see every single step as we transition from the summation notation through the factorials to the ultimate computation. Of course, when you do that for yourself, you'll probably skip a couple of steps here. Okay, now what does that look like? Well, here is e to the 2x, and here is the fourth Taylor polynomial, and we can see that the fourth Taylor polynomial really is a pretty good match for this function, at least for quite a bit longer than the straight line, the first order approximation, the linear approximation would be. Now, of course, if we want to have a good approximation that is farther away from the origin, say somewhere around here, then the fourth order Taylor polynomial isn't good enough. And so the next kind of task that we can set ourselves is to compute arbitrary Taylor polynomials of a function at a equals 0 again. I'd like to expand around a equals 0. That makes some computation easier. And so for this next example, we are looking at the Taylor polynomials of the cosine function. Again, well, what do we need? We need derivatives, right? So the function is cosine x, which gives us a value at 0 of 1. The derivative is negative sine of x. The value at 0 is 0. The second derivative is negative cosine x. Its value at 0 is negative 1. The third derivative is sine of x, which has a value at 0 of 0. The fourth derivative is the cosine of x, and the value at 0 is 1. And of course, after that it repeats because we're back at the start. So if we want to have an arbitrary Taylor polynomial, we now need to find a pattern in these derivatives. And that's another one of those hiccups that I mentioned earlier. And that one is genuine because seeing these patterns is something that takes some getting used to. For the cosine function, I would hope that it won't be that bad, and we'll see another pattern recognition in the next example. So this pattern repeats, and that means that the odd numbered derivatives are 0. And so a standard trick for that, and again, it's one of those standard tricks, once you have seen it and are used to it, you will remember it. If not, it takes a little bit. But basically, we only have to focus on exponents of the form 2n. We only have to worry about exponents that are even numbers, because we know for the odd numbered exponents, we get 0. That means we only have summands that involve the terms x to the 2n over 2n factorial, and we still have to figure out what the 2nth derivative of the function is. The even-numbered derivatives go from 1 to -1 to 1 and so on, so the even-numbered derivatives at 0 are 1 and -1 in alternating fashion. And alternating negative signs, again, standard thing, if you see it for the first time, you want to make a mental note. Alternating negative signs are typically represented by a -1 to the n or a -1 to the n plus 1. And in our case, for n equals 0, we get 1. For n equals 1, we get -1, so we need -1 to the n, because that for n equals 0 gives us 1, and for n equals 1 gives us -1. So for this one, -1 to the n works. And so that means the n equals 2kth. So we're looking at an even order, the 2kth Taylor polynomial of the cosine function about a equals 0 is t2k of x, sum n equals 0 to k, 2nth derivative divided by 2n factorial times x to the 2n. Okay, so that's one big old hairy formula, but what we get out of that formula is that now we can look at the Taylor polynomials sequentially. So we're starting with the most primitive one. The 0th Taylor polynomial is, of course, just a constant. It's just horizontal. and that's actually also the tangent line here. That's just one of the interesting properties of the cosine function. If we go to second order, then our Taylor polynomial is 1 minus x squared over 2. Remember, first order is the same as 0th order, so we're going to skip those. That gives us a parabola that already approximates the cosine function very nicely, right? Also note that the summation goes from 0 to 1 because we're going in steps of 2 already in here anyway. That's encoded into the formula. If we're looking at the fourth order Taylor polynomial, we get an even better fit. Sixth order Taylor polynomial gets longer. You can also see how these polynomials get more and more complicated, but we get a better approximation again. And so now if we don't write those polynomials down anymore and just record the order, we can see that as the order of the Taylor polynomial increases, we get a better and better approximation of the cosine function on longer and longer intervals. And that is the idea behind Taylor polynomials. That is the idea behind numerical approximation. I think I've got one more here. Yeah. The 18th order approximation now approximates pretty well, and now we could actually start talking about, well, how much is the error in here? It's not visible anymore, but there still is an error, and we could start talking about how do we make this error smaller than 10 to negative 8 or 10 to negative 17, whatever the accuracy of your computer arithmetic is. We'll talk about that in the error analysis. Before we go there, however, let's talk about the Taylor polynomials of the logarithm function, which has a different kind of pattern recognition, and which is expanded about a equals 1, because of course you can't expand the logarithm about 0 because the logarithm is not defined there. Okay, so again, we first need derivatives. First derivative is the logarithm, the zeroth derivative is the logarithm. The first derivative is 1 over x, the second derivative is negative 1 over x squared. The third derivative would be 2 over x cubed, and what you really want to do here as you are recognizing a pattern is you don't want to simplify too much. So you've got the plus, minus, and then the negative sign cancels. Okay, so that's a plus again. But don't multiply these things out because we can already see here these powers will keep shelling out the next number, and we're going to generate a product that is similar to a factorial, right? So the third derivative will be negative. It'll have a 3 up here and a 4 in the denominator. And so the fourth derivative is negative 1 times 2 times 3 divided by x to the fourth. The fifth derivative, again, the sign goes back to plus. The fifth derivative is 1 times 2 times 3 times 4 divided by x to the fifth, and so on. So what do we see in this pattern? This exponent is the same as the order of the derivative, right? So the nth derivative should have an x to the n in the denominator. This product here goes up to 1 less than the order of the derivative, right? 3, 4, 2, 3, 1, 2. So we should have an n minus 1 factorial in the numerator. And the signs are alternating, so we need a negative 1 to the n or a negative 1 to the n plus 1. And since at 2 it's negative, we should probably have a negative 1 to the n plus 1. We probably cannot encode the zeroth derivative in that pattern, and that is just as well, because of course at a equals 1 that zeroth derivative, the logarithm of 1, is 0. Okay, so what does that tell us? That tells us that the nth derivative is negative 1 to the n minus 1, 1 times 2 times 3 times 4 all the way through n minus 1 divided by x to the n, which is negative 1 to the n minus 1 factorial divided by x to the n. So that means the nth derivative at 1 is negative 1 to the n minus 1 times n minus 1 factorial, because the denominator is just 1. And that means the capital Nth Taylor polynomial, we start the sum at n equals 1, not at n equals 0, because we already know that the zeroth derivative is 0, is the nth derivative divided by n factorial times x minus point of expansion, x minus 1, raised to the n. And now here we can also see, again, getting used to working with factorial functions. N minus 1 factorial divided by n factorial, well, that's the product of the first n numbers, that's the product of the first n minus 1 numbers. The only thing that survives here after cancellation is an n in the denominator. And so our nth Taylor polynomial for the logarithm is negative 1 to the n minus 1 divided by n, x minus 1 raised to the nth. And we can look at those now, and we see that the first Taylor polynomial is the tangent line, the second Taylor polynomial fits better, the third Taylor polynomial fits even better, the fourth Taylor polynomial fits even better, and so on and so on. However, what we can and do see, let me just scroll all the way and then one more than I need to, what we see is even though the fits get better, we don't get a good fit at the left end because, well, the logarithm goes to infinity and you cannot model something that goes to infinity with a polynomial. That is not a surprise. However, we also don't seem to be able to get a fit that is good past x equals 2 here. And that is a little bit surprising because, after all, the function looks perfectly fine here. The reason for that is that Taylor polynomials converge on symmetric intervals, which means if the Taylor polynomial cannot give a good approximation beyond 0, then it also cannot give a good approximation beyond 2. And that is something that is actually quite deep that we're not going to be able to discuss in detail. And as I mentioned to you, and as you may have also seen, we're looking at quite a few things here where it isn't necessarily that things are hard, but there's quite a few details we have to keep track of, and there are some things that you have to dig out that were hard to begin with, such as computing nth derivatives. And so if you want to take a break, then right now is a good time to just hit the pause button. We're going to continue with the error analysis, which is intended now to explain why it is that Taylor polynomials sometimes approximate really well, such as for the cosine function, and why they sometimes don't approximate so well beyond a certain point, as is the case for this logarithm function here. So I shall move on. Use your own best judgment what you want to do. We ride. Okay, so we also, once we can see this phenomenon that Taylor polynomials have the potential to be good approximations, we want to know how big the error is, and ideally we want to control the error. So at least in some interval, Taylor polynomials always get closer to the function as we increase the degree. And that is true except in pathological examples that you can see in an advanced class, but they really take some constructing, so we're not going to mess with them here. So how do we quantify this error? Well, on one hand, when you are given the Taylor polynomial, like that fourth Taylor polynomial we worked out in the first example, we may want to know how close that polynomial is to the actual function in a certain interval, and that is what is called an a posteriori estimate, an after-the-fact estimate. If you can't change the order of your approximation, all you can do is figure out how good the approximation is. On the other hand, when somebody just gives you a function and says, I want to have a certain quality of approximation, then we want to know how high we have to choose the degree of the Taylor polynomial so that the Taylor polynomial will not be too far away from the function. And that is an a priori or a before the fact estimate. This is where somebody gives you design specs and you just sit down and work out how to design your Taylor polynomial. And the next result on the next panel is really the key to both the a posteriori as well as the a priori estimates, and we're also going to see examples for that. So the theorem is if the function f is n plus 1 times differentiable near a, so for x minus a absolute value smaller than some kind of radius, remember these Taylor polynomials converge on symmetric intervals, then the difference between the function and the nth Taylor polynomial for x minus a absolute value smaller r, so on that short interval, on that symmetric interval, is bounded by f of x, well it is f of x minus tn of x is less than or equal than some number m, that's the one that takes some explaining, divided by n plus 1 factorial x minus a to the n plus 1. So first of all, we see that this term is very similar to the terms in the Taylor polynomial, except for this m, this mysterious m here. And that m is in fact also very similar to the Taylor polynomials, because capital M is such that for all x minus a absolute values smaller than r, we must have that the n plus first derivative of the function is smaller than m. Okay, now basically what does that mean? Well, okay, for most of our mathematical careers we have worked with equations and we're used to things being exact. Now all of a sudden we work with inequalities and things are no longer exact. And in fact, usually when we do this kind of stuff, exact work is impossible. So we have to get used to working with inequalities. That is another one of those hiccups that I've mentioned. The other one is getting used to this m here. I'm not sure if that's on this panel. Moreover, computing this m is not an exact science. So let's first of all think about where this m comes from. Basically, we have seen that the more derivatives we match, the better an approximation we get, right? And so the nth Taylor polynomial, the first derivative that the nth Taylor polynomial doesn't match at that point of expansion is the n plus first derivative. And so it should make sense that the larger the absolute value of the nth derivative of the n plus first derivative is, so the more n plus first order curvature, if you will, we have, the worse the approximation will be, because that big curvature, even though we match the first n orders of curvature, that big n plus first order curvature would pull the function away from the polynomial. So that's why that m makes sense. But then also computing this m is not an exact science. In fact, on an exam that I once graded, a student wrote down m is evil because he didn't like the computation, and he was entitled to that opinion in my book because he computed m correctly. So basically, if after you know how to do this stuff, you come to the conclusion that it is hard, I will not disagree with you. It is a challenge, but until we get there, we might as well just roll up our sleeves, put on our hiking boots, whatever we need to do in order to get through this. So computing the m is not an exact science. Yeah, we could really obtain really good estimates for this m, but once we have a number that is, say, less than 10%, that is within less than 10% of the best m, we're going to only use estimates. Once we've got that, effort really would better be spent on improving the approximation, or the way to estimate the error to get a better error formula maybe, than on improving the m. And we're going to see how to estimate that m in the examples, of course. So let's first start with a fixed degree Taylor polynomial. We want to estimate the difference between the function f of x equals e to the x and its 10th order Taylor polynomial for x minus a smaller or equal than 3. Okay, so that difference is bounded by this error formula, m over n plus 1 factorial x minus a to the n plus 1. And that means we need the 11th order derivative of e to the x, which, thank goodness, is just e to the x, right? So these problems also have to be chosen carefully. If the derivatives are ugly, you'll never get done. And because the exponential function is increasing on the interval x minus a smaller or equal than 3, so x absolute value smaller or equal than 3, that would be the interval from -3 to 3, e to the x is increasing, so m really is just e to the 3. That's an upper bound for the 11th order derivative of e to the x on -3, 3. That means that now the difference is smaller or equal than e cubed divided by 10 plus 1 factorial x minus 0 to the 10 plus first, which would be e cubed divided by 11 factorial times 3 to the 11th, and that is not something that you compute by hand. It's approximately 0.09, which means that even in the 10th order approximation, the only digit that really is fully reliable in the values we would get from the 10th order Taylor polynomial is the first digit. Well, but at least we've got one good digit. Now, what you then certainly can ask yourself is, how do we get an approximation that has better quality? How do we get an approximation that gives us 8 correct digits, for example? And so that's what this next example does for the cosine function. So we want to find the smallest possible n, so that for f of x equals cosine x, expansion about a equals 0, and x minus a smaller or equal than 2 pi, that's more reasonable than many other things, because of course the trig functions scale in terms of pi. We want to have that the error is at most 10 to the minus 8. Well, the error is bounded by the error formula, m over n plus 1 factorial x minus a to the n plus 1. If we can now make this error formula smaller than 10 to negative 8, then the error itself will also be smaller than 10 to negative 8. And so this exclamation sign there says we make this error formula, this error estimate, smaller than 10 to negative 8. How do we do that? Well, we first of all need to find the m. And the absolute value of the n plus first derivative, we don't know what it is, but we know that the derivatives are sines and cosines with negative signs thrown in according to the pattern for sine and cosine. if we take the absolute value, those negative signs don't matter. So the n plus first derivative is either the absolute value of the sine function or the absolute value of the cosine function. Well, that means m equals 1 should work because sine and cosine don't exceed 1. So that means that the error is bounded by the m over n plus 1 factorial x minus a to the n plus 1, which I should probably say less than or equal here, but we can just set that equal to 1 over n plus 1 factorial 2 pi to the n plus 1, and we make that smaller than 10 to negative 8. And now, of course, in the world that we are used to, we would try to solve for n, and for something this complicated, that just doesn't work. So what we really do is just trial and error. You use a computer algebra system, a calculator, or a spreadsheet, and just compute this term for various values of n, and it turns out that for n equals 29 is the first time that this term is smaller than 10 to negative 8. So this is just straight computation, straight with numbers. After all this theory and patterns and all sorts of other things we've done, you just punch in numbers into a calculator or a computer until you get a number that is smaller than 10 to negative 8. And so n equals 29, that means for the cosine about a equals 0, okay, for the cosine about a equals 0, that's the same as n equals 28, because the 28th and because the 29th derivative of the cosine at a is 0. But basically what that means is that we need a 28th order Taylor polynomial to get this quality of approximation for the cosine function, which is lengthy, which is not something that you would want to compute by hand, and certainly you will also look for ways to get away with fewer n's, because, or with a smaller n, because after all this error formula may be a worst case situation, but that is left for more sophisticated analysis that we're not going to do here. But with this polynomial, you can now compute a trig function at basically an arbitrary value, because you can compute it anywhere between 0 and 2 pi. And you can do this with elementary operations without triangles and all sorts of other things. This should be the final example here, which shows that this formula really is a worst case estimate and can also go wrong. We want to find the smallest possible n so that the logarithm function expanded about a equals 1 and an interval of width of radius 1/2, that the error for that is at most 10 to negative 8. Well, okay, again, the error is smaller than what we get guaranteed by the error formula. We set that smaller than 10 to negative 8. First thing we have to do is find the nth derivative, but we already know that, right? We know that the nth derivative is, or the n plus first derivative is negative 1 to the n factorial divided by x to the n plus 1, and that's because the nth derivative was negative 1 to the n minus 1 factorial x to the n. That's not something that I know offhand, but that's what we did in the example on the Taylor polynomials, right? If necessary, scroll back to that. Okay, and so the absolute value of that would be that because the largest value, the smallest value, okay, now we have to be careful here. We're dividing by x, right? Which means a small denominator makes this thing larger. The smallest denominator we can have is that we step 1/2 to the left of 1, so we would have a denominator of 1/2. And if you have a denominator of 1/2, well, the negative sign goes away, and your number becomes 2 to the n plus 1 times n factorial, which is this m that should work. Okay, so now we take our error, smaller or equal than the error bound. The error bound is 2 to the n plus 1 capital N factorial divided by n plus 1 factorial times 1/2 to the n plus 1. So we are saying that this is, the farthest that we can get away from the center is 1/2, so that's 1/2 to the n plus 1. And well, now we can see something here. The 2 to the n plus 1 will cancel with the 1/2 n plus 1. The n factorial will cancel with the n plus 1 factorial. We end up with 1 over n plus 1. Well, if I said 1 over n plus 1 smaller than 10 to the negative 8, on one hand, hey, yeah, I can solve that. But look at the solution. The solution is terrible. I mean, it's totally unrealistic to think that we would ever compute a 10 to the 8 plus first order Taylor polynomial, right? So that means that, yeah, there is a problem, and so there certainly are further things that need to be done, and these things are being done either experimentally or through complex analysis, because we would certainly need a better way to estimate the difference between the logarithm and its Taylor polynomial, or just a better way to approximate the logarithm. And in fact, might as well weave that in right here. Since the earliest days of computing, logarithms were not approximated with Taylor polynomials. Logarithms were approximated with lookup tables, so very much with tables like you make t-charts for functions. You just write down the values and the images, and that would just be programmed in the operating system. Moreover, note that when x minus 1 is greater than 1/2, if I had something greater than 1/2 here, I would keep an exponentially growing term divided by n plus 1, which means the estimate does not converge to 0 at all, even though it can be shown, as we've also seen in the pictures when we did the Taylor polynomials, that the difference ought to go to 0 even for the difference between x and the point of expansion between 1/2 and 1. Okay, so there is a good bit there that still could and should be done, and we leave that for advanced classes. For now, the main point for this presentation was and is that we have a first idea of what Taylor polynomials do and how numerical approximation works. So let's close with this. We can talk about approximations in science and engineering, and in fact, quite often, especially in physics, I have seen it, where people talk about functions being approximated with a truncated Taylor series. And that sounds really mysterious, right? What's a series? And what do you mean by truncate? Well, okay, so from an abstract point of view, that makes sense, first of all, because once you know what Taylor series are, and they are infinite Taylor polynomials, yeah, okay, if a series is an infinite Taylor polynomial and you truncate that thing, you're back with a Taylor polynomial, right? So that means, yeah, when you truncate this infinite Taylor polynomial, we end up with a finite Taylor polynomial, and that's what we just discussed. So basically, quite a few times, if this more complicated language, which actually has a solid abstract base also, when that is being thrown around, if you haven't quite seen all the abstract stuff behind it, it can help to think of just a Taylor polynomial of a high enough degree when people talk about a truncated Taylor series. In fact, most often, especially in the early classes that you might be taking concurrently to this class, when people use a truncated Taylor series, they often just talk about a linear approximation. They just talk about a tangent line, or at worst, maybe a second order approximation. So don't get tripped up by fancy language. That is certainly never good, because language can always be learned. And yeah, as you can see here, if we take this approach, then we do sidestep a good bit of technical machinery on infinite series, and it's just as accurate as what we would say otherwise. On the other hand, we started this whole approximation with this question, well, how do you compute e to the x, and how do computers compute e to the x? Well, the Commodore 64 back in the day, and well, I'm not sure if that's an advertisement, because I'm not sure if you could even buy those things anymore, but that was the machine that I'm familiar with. That's the machine where I even read large parts of the operating system. That Commodore 64 really did use Taylor polynomials to represent e to the x, as well as various kinds, or as well as various trigonometric functions. It was really interesting because it just had a routine that computed polynomials, and then it had a separate place in the operating system where the coefficients were stored. But that certainly was back in the day, right, when 64K of RAM was considered amazing, and well, you had to get the 64K of RAM on this machine by deactivating the operating system, actually, because part of the operating system occupied the same addresses as that RAM. So yeah, war stories here, right? Old guy talking about the early days of computing. Great, yada yada yada. You now have cell phones that have 1,000,000 times the power of that thing. Maybe not 1,000,000 times, but quite a bit more power than that. So today's systems are more sophisticated. However, the basic idea stays the same, and even, or especially in supercomputers, the approximation is done with certain rational functions, and we're using different functions in different places. Basically, we do this piecewise. The idea being that even though it requires more programming and more drive space and a case analysis, and you have to store more coefficients and so on, if you can get away with computing a function like e to the x with, say, a rational function that requires, say, 10 operations, as opposed to a polynomial that requires 50 operations, well, then you need fewer processor cycles, fewer floating point operations, and that is where the speed is, right? Memory concerns really aren't that big anymore because hard drive space as well as RAM has, of course, gotten huge since the early days. I'm pretty sure the programmers of the early machines would have loved to use faster approximations also, but they were constricted by the amount of memory that they have, and so they couldn't do that. So it's actually very nice to have more room to work with in these wonderful new machines that we have here. So if anybody tells you that, yeah, you've got all those wonderful machines and you're getting soft, well, no, I mean, it's nice to have computing power and room to work with as long as you can still write really tight code. The idea, however, is the same though, right? In both cases, we are using functions that are easy, or at least easier to compute than these abstract functions, and we are approximating these abstract functions then with these easier functions. And so this now closes a huge circle, right? We started with approximation of functions that we really didn't quite know how they are computed. Let's be honest with that. And we now know how they are computed. If not in detail, then at least we have a way to compute them in principle. And I think on probably machines that are restricted in their memory, such as graphing calculators, Taylor polynomials are probably still used for quite a few functions, except for the logarithm, which we have seen in some ways fights back. And so we understand that now. As we have gone through that, we have reviewed higher order derivatives. We've familiarized ourselves again with the factorial function. We've talked about summation notation, and we've done this error analysis where we have to compute these higher derivatives and then estimate them. So we've got a lot of really cool stuff to work with. You've got a good bit to think about, but I would say you think about that and then start hitting the homework, and as soon as you get into the groove of computing those polynomials as well as approximating these errors, you will hopefully agree with what I said at the beginning of this presentation, which is that once you've got it all in place and once you realize that you really can juggle all those pieces around, it really ain't that bad. Okay, I hope you'll get there. If not, office hours, email, and so on, we'll do what we can. Cheers.